So I just,
Okay.
one quick comment is the traditional definition of Stirling numbers of the first kind doesn't have the signs. It's the numbers you
Yeah.
have times -1 to the distance from the diagonal.
Okay. So that settles the the sign business and
And
yeah,
in
the
particular,
combinations.
they are very combinatorial. They're counting an explicit set.
Okay. Okay. Yeah. I think I used to know this a couple of years ago, and now, as always, these things have faded in my. But yeah, there's different convention for what those Stirling numbers are. I'm not sure that one is dominant on the others. So I have adopted the one that I found in the combinatorics books. I do that. Let me give an attempt to prove this thing. So the recursion is a no, corresponds to this differential equation. Actually, let me see. Yeah, so the result is that this satisfies the differential equation and the initial condition. And if you can do that, then you're done. And it would seem that at least checking the initial condition should be straightforward. But I didn't find this job particularly straightforward. Even verifying that the expression equals 1 for z equals 0, that this gadget is 1 if set equals 0, I found it challenging. Now, even for this, now if you plug it in, you're reduced to this binomial identity, and what do? Actually, I used to give these talks 1 year ago, and then I would then launch into a story about the fact that I had to do a library search, and no, eventually I found the formula, and in fact I found it in some very, very old manuscript. It's a famous formula in the end. Someone else had found it useful. I'm quite sure that if now you feed this into ChatGPT 5.2 Pro, it will just do it for you. But so the situation has changed a bit. Just not too long ago, the only way I knew how to do this was to go to a library, put myself in front of the shelf with combinatorics book, and open them until I found the formula, which fortunately I did. Now, how would you come up with the formula? No, once you have the formula, no, you can probably, no, with enough time, prove it. But how do you come up with the formula? And I can rewrite history and tell you how you could come up with it. Now, Manin has this functional equation for the generating function. And then you can postulate that this m is n times w. Why not? No, you can do whatever you want. And this might suggest to set n equal to that. No. Why? Because then you'll have some cancellation. Now, if you divide by n to the l, then you get this. You get whatever w is, w to the l must equal this business. And if you rearrange the terms, this is what you get. W is some magic series such that w to the l minus 1 times w inverse is this very specific gadget. And then you have to come up with the following. This is a fact. Now, if y is x minus 1 times x to the minus m, then it just so happens that x to the m is this series involving y. How do you come up with this? Yeah, where do you find it? Well, there's an exercise in Paul Jazzego, so I have the feeling that 100 years ago people would look at this and know exactly what to do, because this was an exercise in a standard textbook for becoming proficient with handling these formulas. It can be proved with Lagrange inversion. Eduardo Nascimento, one of our collaborators, was very quickly able to do this. Once you have this, then you take m equal 1 over L and x equals w to the L. These were positions, and this is what you get. Y is x minus 1, x to the negative 1 over L. No. That becomes WL minus 1 W inverse, and the right-hand side is what I know about W from the previous, from the functional equation. Okay, so at this point I have this. It's in the form of the lemma at the top of the page, and therefore I can write a series for it. I mean, and this is equivalent to the formula in the claim. So there you go. This is what one might have done, and if one were proficient with these combinatorial formulas and this Lagrange inversion or whatever, this would probably be a very natural thing to do, and starting from the functional equation you would get the formula that then implies everything else. All right. So that's the proof. Now, I am very proud that in this talk I can give a proof of something. So modulo knowing these identities, it produces the formula that then implies the Stirling number formula. Okay. Now, where to go from here? This is where I will cut it real short, but one can dig a lot deeper into this guy. I mean, even numerically. For example, you could study the generating functions of the fixed Betti number. You think k, and then you want a generating function for the 2k Betti number of m0 n bar. And the natural thing to do it is to put it in this form as a generating function. So long before knowing about the formula for m0 n bar, we were able to observe this. This generating function has a reasonably simple formula, just exponential with coefficients that are polynomials, polynomial coefficients. What can you say about these coefficients? Well, you can tell what the degree are, and we observed in the first approach to this that all the coefficients seem to be positive, and then having formulas around like what we got for m0 n bar with the formulas we've been talking about, then you can prove that actually these are pretty positive. I'm not sure that this would be a satisfactory proof for Allen. I mean, it's not a very conceptual, it's just very brute force verifying that these things happen to have positive coefficients. What do they look like? Well, P0k is a constant, and that's what it is. And P1 is the beginning of an exponential, and then it's no longer so. I mean, but that's enough, for example, to write f alpha 1z. Alpha 1z must be this. You see e to the z, P01, e to the z minus P1, 1z. This is what this formula looks like in that case. Very simple. There you go. This is the generating function for the second Betti number. So it's this diagonal in the basic picture I've been drawing. Now, I was very tempted by this conjecture that all P and Ks are log concave. And in case you have not run into log concavity recently, this is what it is about. If you have a polynomial with coefficient, you say that it's log concave if there's this inequality for every I. Now, the square of a coefficient is at least equal to the product of the adjacent coefficients. There's a natural stronger condition called ultra-log concavity, and I will come up, I think I will get to it before the end. Log concavity is one of those amazing things that show up in all sorts of places. There are hundreds of pages of reviews of appearances of log concavity in many combinatorially significant situations. There's a beautiful review article by Stanley I can certainly highly recommend, and there's more recent updates to that survey article. One beautiful example is the first theorem that Jun Ha proved as a graduate student. As a first-year graduate student, he proved that the chromatic polynomial of a graph is necessarily log concave. This had been conjectured many years before. And, Jun Ha has this very powerful point of view. The log concavity is indication that something deep is there, and a Kähler package may be there and justify why something should be log concave.
So, Paolo, there is a question from Teddy Gonzalez. In what generality is the expansion of a variety in L palindromic?
In what generality? I don't know. I mean, if your variety happens to be mixed state, so it happens to be a priori a polynomial in L, and if it is a smooth projective, compact projective variety, then it will be palindromic just because the Betti. Well, actually, no. So the honest answer is I don't know of a very general statement in this sense. No, there are situations like the situations we're looking at in which it is clear just because you're dealing with a smooth projective variety and the coefficients of the polynomial are just the Betti numbers, but that depends on the outcome algebras here and stuff like that. Good question, I just don't know. Okay, so I was going to advertise the conjecture that these objects may be log concave. No. as a consequence of the Stirling formula, of the formulas that I talked about so far, you can prove that this is true. No. So basically, as much as your computer will allow you to do it. But for all case, no, for every Betti number, these polynomials, these polynomials are log concave, at least in this range, and I don't see any reason why the range should not be larger than this, except that I've learned not to trust this kind of evidence, so this is a little story that has to do with this. Now, as we were studying these polynomials, it turned out that the coefficients of the polynomials are determined by some other polynomials, this gamma mjt, and the only reason why I'm bringing this up is that the first several hundred of these have positive coefficients and are log concave, and if you're a reasonable person or a physicist, you might think that that is enough to conclude that they are log concave, but in fact they are not. So gamma 20 would be I think the 400th polynomial would write, and it turns out not to be log concave. And then you look at the next one, it's not even positive coefficient. So what I'm trying to say is that overwhelming evidence is maybe not worth much. So the fact that we were able to prove that this is true for n between 0 and 100 and all k doesn't really convince me that these are log concave. I think this conjecture is, if it is true, there must be a very good reason why it is true, not just some brute force computation. So maybe it goes back to some kind of consideration such as Juni Ha has in his work. All right, so yeah, I was going to conjecture that. Fortunately, my computer told me I should not conjecture that. Let's see, what's the timing? At this point, I'm down to contextual remarks, so stop me whenever you want me to stop. We took a little break. I don't know if you want to stop now or if I can go on for 5 more minutes or so.
Well, you have 5 more minutes only.
Okay. So there's something that occurs here. I did not know the existence of the Lambert W function before running into it in this project, but it is the solution, in quotes, because there's different solutions of this equation. Wt times the exponential of Wt is t. And this there's a survey article by Percy Diaconis and others with beautiful applications in all sorts of contexts. Applied mathematics says, this shows up all the time. Apparently in combinatorics it has many applications. Here's a combinatorial observation. If you take negative Lambert W of negative t, what you get is the function that counts rooted trees. So I'm writing unsurprisingly because Manin's work was all about generating functions counting trees. So, and maybe this is why this function turns out to make our expressions a little easier. Now, if you adopt this tree function and put in some extra information, so t now is the tree function applied to the exponential of zl, then there are just polynomials that allow you to write a very simple expression for your generating function we've been talking about for the Grothendieck class of M0 and bar. No, this is more combinatorial identities that involve Stirling numbers, and these polynomials are very interesting to look at. I think they would deserve to be studied a little further. One thing that this gives is asymptotics, so you can this tree function, the negative Lambert W negative t, goes like this. For as n goes to infinity, it will look like this particular series. So, for example, out of this asymptotics, you get ultra-low concavity, asymptotic ultra-low concavity for the Poincaré polynomial. These extra denominators correspond to a stronger condition called ultra-log concave. So this says that these polynomials are asymptotically, if you wait long enough, ultra-log concave. Again, these kind of things don't happen by chance. There must be a better reason for that, or a conceptual reason, not just brute force computations. Now, asymptotic, the result of that is attributed to Newton. It kind of seems a little silly to attribute something to Newton, but apparently somewhere in Newton's writing there's the observation that real rooted polynomials are ultra-log concave. So it's natural to conjecture that the polynomial, the Poincaré polynomial for the even Betti numbers has only real zeros, and once we made a conjecture, we found that other people had made it, and particularly I want to mention Luis Ferroni. So it's an interesting. No, I was a little amazed, but if you can easily write the polynomial for n equals 100, and you ask Maple to compute its roots, and it will find real roots. It's kind of amazing. And there is a big context, which is why I want to mention this, from combinatorics, that somehow makes it, I don't know, if not believable, at least, I don't know, it gives a context to it. The context is the following, and it just so happens that H2 star or M0 n bar is the Chow ring of the braid matroid. You may or may not be familiar with the fact that matroids, these combinatorial objects, have Chow rings. That's a very beautiful discussion that is not this talk. This happens to be the Chow ring of the braid matroid once you use something called the minimal building set. And it follows from Kapranov's construction of zero and bar. The conjecture that Ferroni and Juni Ha independently made was that the Chow polynomial of every matroid with respect to the maximal building set, so somehow the other end of the scale, should be real rooted. So what we are observing is that in this case, for M0 and bar, real rootedness seems to happen for the minimal building set. And that's a little strange because it's very easy to have examples of matroids for which the minimal building set will not give you real rooted polynomials. So that's the question. What's special about the braid matroid? All right, so now I want to really wrap it up because my time is up. Let me just mention a few recent additions to the literature. There's beautiful work from last year of Choi, Kim, and Lee, where they can establish log concavity in a broader context. So they recover the asymptotic log concavity I had a couple of slides ago. There's another proof of the formula in terms of Stirling numbers that fits in the context of polymatroids with respect to arbitrary building sets, and that's due to Luis Ferroni, Chris Materno, Pagari, and Betti, also from last year. So again, this generalizes formulas from the Poincaré polynomial that I put on the slides earlier. Then Mike Watt on Nascimento was able to improve the asymptotics by using the new formulas. And very, very recently, this is from January 26, so a couple of weeks ago, there's this very beautiful paper, again by Choi and Kim, where they proved that the Betti numbers for the moduli space M0 and bar are asymptotically normally distributed, which is something that if you plot them, you start suspecting. You have this beautiful, if you plot the Betti numbers, you will find a nice bell curve that suggests that this might be the case. They were able to prove it, at least asymptotically. All right, I think this is just a good time to quit. Thank you. Thank you for your attention.
Yeah, let's thank Aluffi. Very nice talk.
Thank you. Thanks.